This Earth has only one natural satellite, but we have made do very well with this, our lone moon. It is interwoven in man's history, its waxings and wanings long ago recorded on calendars. What now compels modern man to fly to the moon? There is the great urge of discovery and exploration, for exploration has always opened new, unexpected horizons to our view, and opened undreamed of frontiers of economic development, technology, and social well-being. But in setting foot for the first time on this heavenly body, we are not simply discovering a new chain of mountains. There is a greater opportunity before us. The moon is a vast natural laboratory existing much as the Earth did billions of years ago. For the moon is without an atmosphere. It is without weathering and erosion, two forces which have reworked the face of the Earth and obscured its remote past. It is a laboratory we could never build with all our hands and all our tools. We can fly scientists and scientific instruments to this laboratory. We can study the origins of the Earth and perhaps of the universe. A flight to the moon in the space age is not long. 2.5 days to travel back in time 5 billion years. This is a voyage of exploration that man must make. We cannot draw a straight line from the Earth and fly along it to the moon. The moon is moving around the Earth at 2,300 miles an hour. The Earth is revolving around the sun at 67,000 miles an hour. Both are revolving on their axes. We must fly between 2 points constantly changing in space. For the manned flight, we have chosen a free return trajectory to the moon. This means that the spacecraft is fired from orbit to the moon in such a way that it will loop around the moon and return without further power being applied. Normally, of course, we will insert the spacecraft into orbit at the moon's equator and land at a pre-selected site. We choose a launch time and trajectory so that the crew will land in daylight. The sun will strike the site at an angle of 7 to 20 degrees. This gives the crew visual perception to avoid obstacles when landing. Preparation for launch will begin here, the Vehicle Assembly Building at Kennedy Space Center. A vehicle assembly building provides protection against the weather during most of the pre-launch checkout period. It is almost 44 stories high and tall enough to check out an Apollo Saturn V space vehicle on its mobile launcher. The assembled space vehicle travels to the launch pad 3.5 miles away on a transporter crawler. This is the command module, living quarters of the crew. The mission commander is in the left couch. His crew, a command module pilot in the middle couch, and a lunar module pilot to the right. The command module contains all systems critical to piloting the flight once the spacecraft leaves Earth orbit. The second unit is the service module. The service module contains a large propulsion engine. It takes over after the jettison of the big booster. We carry 2 spacecraft in a lunar mission. The second is a lunar landing spacecraft or lunar module. It has separate descent and ascent stages. Below the lunar module, an instrument unit carries a computer and associated electronics. It guides the spacecraft into Earth orbit and computes the trajectory to the moon. The launch vehicle is composed of 3 boosters, plus the instrument unit. Together they are called the Saturn V launch vehicle. Saturn V will launch into orbit 40 times the weight of Gemini, 85 times that of Mercury. Final countdown for the Apollo Saturn space vehicle is conducted from the Launch Control Center next to the Vehicle Assembly Building. At T-minus 30 minutes, the launch escape tower is armed. From this point until it is released at slightly more than 50 nautical miles, the launch escape tower would be fired for emergency escape, carrying the command module to safety. The spacecraft is not launched directly for the moon, but into Earth orbit. The first stage of Saturn V propels the spacecraft to 34 nautical miles altitude and is jettisoned. The second stage takes over. Then a structure between the first and second stages is jettisoned. In this period, too, the launch escape system is jettisoned. From now on, the crew can fly the spacecraft safely back to Earth if necessary. After the second stage is jettisoned, the third stage takes over and inserts the spacecraft into a parking orbit 100 nautical miles above the Earth. At Marshall Space Flight Center, propulsion and stage experts monitor the performance of the launch stages closely. The flight is not yet 12 minutes old. The third stage shuts down, but we retain it in orbit and will use it yet once more. So far, we are on very familiar ground of manned flight, but we are preparing for the unfamiliar. The crew completes their in-flight checkout. If all systems are now go, this man, Flight Director at Mission Control Center, Houston, will commit 3 pioneer astronauts 250,000 miles into space. The decision is made. Over the ocean, the third stage is fired for 5 minutes, and man is on his way. The crew will have little time to reflect on this fact. For 15 minutes later, protective panels will open as the command and service modules separate from the lunar module. Using the service module control jets, the mission commander turns around. He completes his maneuvers and docks with the lunar module. The third stage and instrument unit are jettisoned. The flight to the moon is now in a coasting phase. Velocity in space will average 3,300 miles per hour. The mission commander will navigate, taking star readings as a backup to ground computations. Mid-course corrections from the ground will be made during the translunar flight to maintain the proper trajectory. Just before the spacecraft approaches the moon, the lunar module pilot will transfer to the lunar module and check it out. As the crew swings around the moon, the service module main engine is fired to reduce velocity and insert the spacecraft into an orbit 80 nautical miles above the moon. After a period of preparation, including sleep, the mission commander and lunar module pilot transfer to the lunar module. The command module pilot is left behind to fly the Apollo spacecraft in orbit. The lunar module is separated. 2 automatic firings of its descent engine lower it to the immediate landing area. The mission commander takes over the controls for the touchdown. He carefully brings his spacecraft to a safe landing. But no one opens a hatch and leaps out. The crew must check the lunar module systems and put on special life support equipment. The outside temperature is about 200 degrees Fahrenheit. There is no oxygen in the airless atmosphere. The moment we have waited for comes. 2 Americans stand alone on the unexplored plains of the moon. Surrounded by the silence of billions of years, what will they say? The crew will explore the lunar surface, working together as a team. They return to their spacecraft to replenish oxygen, sleep, and eat. Total stay, about 24 hours. The crew will set up a series of experiments known as the Apollo Lunar Surface Experiments Package, or ALSEP. Once set up, it will look something like these scientific instruments being tested on a simulated lunar surface. The experiments will measure the charged particles of the solar wind, the magnetic characteristics of the moon, presence of ions, and seismic activity. A small atomic generator furnishes electrical power to the experiments. Once activated, a data collection station can transmit 1,060 data bits a second back to Earth and continue to send us this precise information long after the crew leaves. A very important task is collection of geologic samples. 40 to 50 pounds of lunar samples will be flown back in sealed containers. When the exploration of the moon ends, the crew will rejoin the command module. They re-enter the lunar module and fire the ascent engine. The descent engine and landing platform are left behind. The onboard computer will guide the lunar module into an orbit slightly lower than that of the command module. The crew makes the final approach and docks. The 2 exploring astronauts, with their lunar samples, transfer back to the command module. The lunar module is separated and left in orbit around the moon. The flight director at Mission Control will relay the necessary guidance information for the homeward voyage. The service module's main engine is fired, and the crew on its way. The trans-Earth trip is, of course, the reverse side of the coin to the trans-lunar trajectory. Mid-course corrections will be set into the computer from the ground, if required. After more than a week in space, the crew approaches the Earth. About 20 minutes before re-entering the Earth's atmosphere, the service module is jettisoned. Now, all that is left of the original space vehicle is the command module. We aim for a re-entry corridor about 20 miles deep. It begins with the atmosphere 80 miles above the Earth. The re-entry path will be controlled on board by the computer, but manual corrections can be made by the crew. Re-entry velocity will reach about 25,000 miles an hour. As the atmosphere slows the spacecraft down, the crew is protected from the enormous heat buildup by the blunt end of the spacecraft and by shielding around the entire spacecraft. At 10,000 feet, pilot chutes pull out the main landing parachutes, and the spacecraft is slowed to a safe landing speed. It heads for touchdown in the ocean. In one way, this landing is quite different from previous missions. A mobile quarantine laboratory will pick up the crew and take them direct to the Lunar Receiving Laboratory at the Manned Spacecraft Center. The crew will undergo a 3-week isolation period for debriefing and detailed observation. There is a very remote possibility of lunar contamination. The lunar samples will undergo preliminary study for 4 weeks, isolated against Earth contamination. Samples will then be distributed to distinguished foreign and American scientists. These scientists will apply their specialized knowledge for detailed analyses of the samples. Studies will continue for years. And the moon, which has been with us for 5 billion years, will begin to yield up its silent secrets. And this only a beginning.
You're watching Sleepcore. Pleasant dreams.
Have you ever wondered how big the universe is? How many stars are there? Does space go on forever? The answer depends on the shape of space. Let's explore some possibilities. There's an interesting star. This star looks familiar. Haven't we been here before? What's going on? What kind of space is this where we keep seeing the same stars again and again? It's easier to explain in a two-dimensional universe than a 3D one. But what would a 2D universe be like? Let's call it flatland. Life in 2 dimensions has its problems. When 2 flatlanders want to pass one another, they can't go around each other or to the side as we would, since they can't leave the plane. Our athletic flatlanders must jump over one another to continue on their way. The flatlanders live on the one-dimensional surface of their 2-dimensional planet, just as we spacelanders live on the 2D surface of our 3D planet. The flatlanders' planet is orbiting a sun. Their sun is a 2-dimensional disk, just as our sun is a 3-dimensional ball. Like ours, their sun is just one of many stars in their universe. Let's watch the flatlanders explore their universe. They head straight off into space and are surprised to come across their own sun. Perhaps their universe is a sphere and they took a trip around its equator. Or perhaps it's a cylinder. Or a torus. Each of these surfaces is a possible shape for a 2-dimensional universe. Note that we have taken advantage of our 3-dimensional space to see something that 2-dimensional flatlanders can't see directly. In a similar way, 4-dimensional people could draw 3-dimensional universes in their space, but that's another video. We 3-dimensional people can see them without the 4th dimension. We can visualize 3D spaces using only 3 dimensions for our drawings. We first try to understand a flatlander's universe without the extra dimension. Suppose their universe is a torus. We'll save a copy of it, cut the torus once, and deform it into a cylinder. Cut it again, and open it into a square. This square is a fundamental domain for the flatlander's universe. We now see their universe using only 2 dimensions. The flatlanders can still travel about their universe as before. When looking at a fundamental domain, we must imagine that its edges are glued together. Anything leaving one glued edge returns at the other. The way we glue them determines the shape of the space. It doesn't matter where we put the cuts. We need cuts to draw the fundamental domain, but they don't really exist in the space itself. When our cut passes through the flatlanders, they don't feel a thing. What do the flatlanders see in this universe? Their line of sight travels around the universe, and they see the back of their own spaceship. Like the flatlanders themselves, their line of sight can't leave their 2-dimensional space. They see what appears to be a copy of themselves. Indeed, they see images of themselves in many directions. This tiled picture shows what the Flatlanders see and that their universe is boundless. They'll never reach an edge. From the picture of the single fundamental domain, we see that their universe is not infinitely large. It contains only 3 stars and 1 spaceship. It's finite. Neither picture alone gives the full story. By combining these 2 pictures in your mind, you can get a better understanding of the true nature of their space. Now we're ready for 3 dimensions. Take a cubical block of space. We'll use this for our fundamental domain in 3 dimensions, just as we used a square in 2D. We glue the left and right walls. Now the spaceship can travel around this finite universe, passing the same stars again and again. We glue the top and bottom. And finally glue the back to the front. Now the space has no boundary and the ship can travel in any direction. This space is called a 3 torus. Let's ride the spaceship inside the 3 torus. Even though the 3 torus is finite, we have the illusion of flying in an infinite space. There are only 2 stars in this universe, but we see each one over and over. This isn't the only possible shape for space. Before we visit another 3D universe, we'll look at the corresponding 2-dimensional space. Its fundamental domain is again a square. This time we glue the left and right sides with a flip. This surface is called a Möbius strip. When the spaceship takes a trip around, it comes back upside down. The flip makes a difference in the shape of space. A second trip restores it to its original condition. Let's watch the trip again on the original square. Now glue the top and bottom of the square with no flip. What do the Flatlanders see in this space? Looking up, they see the bottom of their own spaceship. Looking forward, they don't see their ship right in front of themselves because of the flip. Their line of sight keeps going across the bottom. When it wraps around a second time, it's flipped again, and they finally see the back of their own ship. The Flatlanders have the illusion of seeing a reverse copy of their universe, followed by a regular one. They see infinitely many images of their universe, half reversed and half not. What if we do this in 3D? 2 pairs of faces connect as in the 3 torus. To make the flip, connect the top of the right face to the bottom of the left face and vice versa. After 1 trip, the spaceship appears mirror reversed. After a second trip, it returns to its original state. Let's see what this space looks like from the inside. As in 2D, we see infinitely many images of our ship. Half are mirror reversed, half are not. When we roll, our reversed images roll in the opposite direction. Life in this space is different than in the 3 torus, where all the copies of the ship move in the same direction, like a flock of birds. We fly this way and see ships in neighboring rows flying in the opposite direction. The mirrored images turn as we do to fly along paths that seem to cross ours, but they can never hit us. That's impossible in this space. We've looked at only a few of the many possible shapes for space. There are other ways to glue the walls of a cube together. Or instead of a cube, we could use a different shape for the fundamental domain. The space we saw at the beginning of this video was really a 3-torus containing only 96 stars. This space is finite but boundless. Astronomers face similar possibilities as they try to understand the real universe we live in, whose shape is still unknown. It is much larger than the simple spaces we've seen in the video and contains vast numbers of stars. But the same principle applies. What seems to be a star in a distant galaxy could be our own sun. The light we receive from it could be light which left the sun billions of years ago, traveled around the universe, and is just now completing its trip. If we can someday find a pattern in the arrangement of the galaxies, then we will know the true shape of space.
You're watching Sleepcore, media for insomnia.
One of nature's most fascinating and efficient construction jobs is performed on Earth by the Urania, or as commonly called, the spider. This 1/20th scale model shows how the Urania's mechanical equivalent, the space spider, might spin a web, actually a large metallic structure in space. Dwight Johnston of the NASA Marshall Space Flight Center, who originated the space spider concept, tells how it would work.
An ideal way to build a space structure would be to build it on Earth, roll it into a compact package, take it into orbit, and unroll it. In essence, that's what we do with the spider concept. The structure is pre-stamped out of one continuous piece of material that would include the truss members, the radial members, and the lateral members. In addition would be a series of coded information would be stamped into the material that would enable the spider to build the structure more economically and more efficiently. The spider uses the coded information for locating the truss members and for also maintaining the proper shape and configuration of the structure. The last act in the processing of the material would be to roll the material into a very compact spool for transporting it into space and for handling once there.
The space spider would be taken into orbit in the bay of a space shuttle orbiter and deployed by means of the orbiter's remote manipulator system. Telescoped for storage aboard the shuttle, the spider then extends to its full working mode. The spider's legs are individually adjustable, providing a capability for lengthening or shortening of truss members, so that a variety of structural configurations can be spun. Two identical segments connected by actuators allow clamping onto a rim or release from it. The spider would be attached to a construction core, which might be deployed previously by the shuttle or spun by the spider itself. Now let's watch the spider as it spins spirals about its core. The stock material taking structural shape as the same sequence of operations is repeated continuously in the spider concept of construction. By fading the spider off the picture, we have a more detailed view of just how the prefabricated material takes on its new configuration and how the trusses are assembled. With each revolution, the structure grows to its desired size. The laser interferometer and corner reflector, in conjunction with the adjustable legs, allows the space spider to spin structures of various shapes. This artist concept shows one of the several configurations of proposed solar power satellites, which the space spider might be instrumental in constructing.
A modified version of the spider could deploy the photovoltaic panels while a spider builds the platform structure. A system of this nature could be placed in a geosynchronous orbit to collect pollution-free energy from the sun and transmit it in form of microwaves to receiving stations on Earth for conversion to energy. The spider would provide the potential for building large systems in modular form. After being placed in their final orbits, these systems might provide electrical power on the order of 5,000 to 10,000 megawatts on Earth, enough to power a city the size of Chicago. The versatility of the space spider is illustrated in this virtually rectangular configuration. One spider is shown laying down the framework, as another covers the surface. Such orbiting platforms might be used for large antennas, solar power satellites, or other purposes. Ultimately, the spider might be employed to build space factories or space colonies for human habitation. Here, one spider assembles a disc-shaped structure, while a second one spins a donut-shaped enclosure. A teleoperator device is shown delivering a new roll of prefabricated material to one of the machines. Metallic structures, spun by a robot in space, as miraculous in a way as the silken web spun on Earth by nature's own Urania.
On the night of February 23, 1987, at the Las Campanas Observatory in southern Chile, Ian Shelton photographed the large Magellanic Cloud. As he developed his plates, he saw a bright object that was not on the previous plates. He thought it was only a flaw, but he walked outside to check it. In the sky, he saw a star he had never seen before. An object appearing so suddenly, he knew must be a supernova. Ian Shelton telegraphed the news of his discovery to the International Astrophysical Union, the IAU. Using global computer networks, the IAU announced the discovery to the world.
Supernova is the most powerful event, the biggest cataclysm one can imagine in the universe. The sun will shine at this rate for about 10 billion years and put out 10 to the 51 ergs. The supernova liberates that much energy in neutrinos in 10 seconds times 100.
Designated SN 1987A, the supernova is located in the Tarantula Nebula in the large Magellanic Cloud, the galaxy nearest to ours. Even though the supernova is 170,000 light-years away, it is the closest supernova since Johannes Kepler saw one in 1604 in the Milky Way.
Supernovae that are visible to the naked eye are rather rare. I think only 3 outside of the present one, have been seen in the last millennium. There was the Crab supernova, now known as the Crab Nebula, which was in 1054 and was even visible during the daylight.
SN 1987A reached a magnitude of 2.9, which is easily bright enough to be seen at night. It once was a faint star called Sandulic -69202, a blue supergiant, about 15 times the mass of our sun.
Well, one of the most important things that a supernova does do is to create new elements. It's a long-standing theory, and I believe this supernova and some other observations have confirmed it, that all of the heavier elements, things heavier than helium, have been produced as a byproduct of stellar evolution, with supernovae playing the dominant role. Now, how does this happen? Well, a star is always subject to its own gravity. So when it has no hydrogen to burn, gravity is going to win for a while, and the core of the star is going to contract and get hotter. And then it will ignite the next fuel that it has to burn, which is helium. It burns helium to carbon and oxygen, and it'll burn some of the carbon into neon and magnesium. And after that, it'll burn oxygen into silicon, eventually silicon into iron in the center of the star, about 1.5 solar masses. Now, it's a quirk of nuclear structure that when you've produced iron, you can't get any more energy out of nuclear fusion reactions. So the core becomes unstable at that point. Gravity is still there all the time trying to pull it down. And now with no fuel left to run on, the core collapses.
Small stars like our sun are not hot enough to burn carbon, and their nuclear fires die out. Then they cool over a period of billions of years to a very dark star, a black dwarf. Heavier stars are hot enough to burn carbon into oxygen, then silicon, and finally into iron. No more energy is available from fusion of iron nuclei, so the star stops producing heat. When the energy source is depleted, the gravity of the star causes the core to collapse inward.
I mean, it falls very rapidly at speeds approaching a third the speed of light. And it collapses in a period no more than a second from something the size of the Earth to an object about 20 miles across.
In this giant nucleus, the protons and electrons of the iron are so close to each other that they combine to form neutrons. Thus, the core of the collapsing star becomes a giant ball of neutrons, a neutron star. If a collapsing star were big enough, its gravitational force would overcome even the forces that hold atomic nuclei together, and the core would become a black hole. Sandulik is probably not massive enough to form a black hole, so it reaches a point where its core cannot collapse any further. At this so-called point of maximum scrunch, the core bounces back and blows the rest of the star out into space with an explosion energy over 10 times the lifetime output of our sun. This explosion is a supernova. The energy emitted by a supernova is primarily composed of neutrinos, particles that very rarely interact with matter. Neutrinos can be detected in huge tanks of purified water, buried in mines in Japan and the United States. 3 hours before the first optical observations of the supernova were made, these detectors noted neutrino emissions somewhere in the direction of the Large Magellanic Cloud. The neutrinos interacted with the purified water and caused flashes of light which registered on arrays of photodetectors in the tanks. These detections were not discovered until later, but they confirmed current theories about how a supernova explodes.
When a star goes supernova, it releases radiation over a broad spectrum at many different times. There's a very interesting portion of that radiation, which is the radioactive decay energy. When the explosion first takes place, the high heat at that time takes lighter elements, such as, say, silicon, and fuses them, burns them into heavy elements such as nickel-56. That radioactive decays then into cobalt-56. And then the cobalt-56 then decays into something that's very common that we all know, that is iron. And in fact, it's thought that a substantial part of the iron that we actually see around us is produced in supernovae. So for a time, say, about 4 months after the supernova itself, all the optical light we see really has its origin in the radioactivity of the cobalt, but that radioactivity is not in the gamma ray region, but it's degraded into optical photons. We see it almost as heat, if you will. Later on, the remnant expands. The optical light curve starts falling off, and at the same time the gamma ray light curve starts picking up, and we start seeing then the radiation coming out as pure gamma rays. So when we're looking then at the gamma rays from the radioactive decay of cobalt, we're actually looking at sort of in real time at elements that have just been produced, say, less than a year before.
In the year following the supernova, several experiments measured 847 keV gamma rays as well as other gamma ray radiation. This included the Solar Maximum mission already in orbit around the Earth, which is run by NASA's Goddard Space Flight Center, and instrument-laden balloons, which were launched in Australia. Some gamma rays from the supernova are scattered, lose energy, and emerge as X-rays or ultraviolet radiation. Japan launched the Ginga satellite, which detected some of these scattered X-rays. NASA's rocket-borne experiments in Australia also observed radiation in this wavelength. Other rocket-borne missions and the International Ultraviolet Explorer observed in the ultraviolet spectrum. Ultraviolet investigations are used to detect atomic phenomena near the outside of the supernova envelope. Infrared observations explore the inside of the envelope and the dust layer of the star before it exploded. These measurements reveal information about the density and temperature of the supernova and the formation of molecules within the envelope and in nearby space. The Kuiper Airborne Observatory, operated by NASA's Ames Research Center, flew several experiments over New Zealand to observe in this region of the spectrum. Since infrared wavelengths are absorbed by the air The experiments were conducted high in the atmosphere.
It's very valuable to continue watching the supernova. In fact, the supernova is going to be watched for years to come. We certainly expect to see enhancements perhaps in the radio region, expect to see perhaps enhancements in the X-ray region, and a real prize would be eventually to see the pulsar that presumably was born when the supernova took place. Right now that pulsar is buried deep inside, and all of us would love to see it eventually, and we don't know. It may be seen in the next year, it may be seen in 10 years from now.
Observations in all ranges of the spectrum were made. Scientists will gain valuable insight into natural nucleosynthesis, the formation of heavy elements. Our solar system was created from these elements. We will gain understanding of the history of the Earth, as well as the rest of the universe, by studying the deaths of stars.
You're watching Sleepcore. Sleep tight.